I just now emerged from a conceptual hangup that's been in the way of me really appreciating the lumen as a unit of light. Radiant flux, I think, is a straightforward idea, the watts of electromagnetic radiation, but photometrically, the unit of luminous flux, the lumen, not so straightforward, even though it describes the human perception of those watts. Should be more intuitive to you and me, but something gets me about it, and I'm going to guess I'm not alone. Let's begin. Radiant flux can vary with wavelengths. I'll use vis-a-vis lambda for the electromagnetic power in each discrete element of wavelength. Integrate this over wavelength to get radiant flux, the watts. Get the watts of visible flux by setting limits on that integral. Now the eye doesn't detect the power at all those wavelengths equally well. The spectral radiant flux, the watts per wavelength, needs to be weighted by the sensitivity of the human eye at each wavelength. Now, sensitivity depends on the probability that a photon will trigger a nerve impulse. That's the quantum efficiency of the eye, but is normalized to something at its peak. It looks here like it might be normalized to 1, but it isn't. And exactly how this response curve is scaled was the crux of my mental roadblock. The unitless function v of lambda is proportional to the response per photon. It has a peak at 555 nanometers with a value of 1. 683 times v of lambda, referred to as the spectroluminous efficacy, is the perceived amount of light per incident watt at lambda. Integrate from 0 to infinity here because any wavelength covered by the photopic curve should be included. And yeah, this is called the photopic curve, proportional to the daytime sensitivity of the eye as opposed to the scotopic curve, the dark adapted sensitivity. I want to talk about vision in normal daylight here. Vis-a-vis is the visible power that the eye detects. It's not the same as the watts arriving at the eye, it's different than that, courtesy of the photopic curve. Vis-a-vis is the luminous flux. It has units of lumens. Now, since v of lambda is unitless, the number 683 must have units of lumens per watt. Now, every textbook has this expression, and it's separately true for each radiometric and corresponding photometric quantity. For example, luminance and radiance instead of luminous and radiant flux. So here's my long-ignored hang-up. Where does this 683 come from? In the simple case of a monochromatic green light source radiating 1 watt of power, the luminosity is 683 lumens. Knowing about that 683 is the difference between this equation being a black box and being something that I can actually understand. There's got to be more to the story, and I went looking. This connection between photometry and radiometry was set in stone by an international standards resolution that defined the candela, which is the unit of luminous intensity, that is, luminous power weighted by the photopic curve per steradian. Now 683, which by the way is an exact number introduced to the world in 1979, is presented here as an immutable scaling factor that bridges photometry and radiometry. The gist of this redefinition from 1979 was that the black body standards that were being used didn't provide the reproducibility of more up-to-date approaches. But the thing is, this 683 figure aligned the candela with the black body standard and was computed for and locked into this new standard as a fundamental given. The origin of 683 is the bit of history that, for me, is the missing link. So Smith gives a description of the lumen in terms of that 1948 definition of the candela, which by the way is 1 lumen per steradian. So Smith puts it, the lumen is the luminous flux emitted into 1 steradian solid angle by a source with the same intensity as 1 square centimeter of melting platinum. Bingo, that's it. You see, this 1948 platinum standard defined the candela as equal to the luminous intensity of 1 square centimeter at 2042 Kelvin, divided by 60. Why 60? Because it takes 60 spermaceti standard candles, preferred for their steady and smokeless burn and stable white flame, to produce the same intensity of light as 1 square centimeter of a black body radiator at 2042 Kelvin. This 1/60th aligned the new candela roughly with this now obsolete English candle power to within a couple of percent. Well, that tidbit sent me deeper, and I found more about those details in this historical piece from 1986 attributing the 60 candle equivalents to a 1937 Standards Committee recommendation, which was eventually ratified in 1948. I'll work with Smith's wording. 60 lumens of perceived brightness is emitted by a point source which has the same intensity as a 1 square centimeter 2042 Kelvin blackbody emitter, radiating into 1 steradian. Let's dissect that. The lumen is a unit of luminous power, or as described here, the photometric unit of radiant power. It's a photometric unit, that is, its power, but weighted by the photopic curve and then scaled with that mysterious 683 lumens per watt. It's defined with intensity, which is the flux per solid angle, in this definition 1 steradian. The thing about intensity is that it only really makes sense when it describes light coming from a point source. The light that this point source sends into this 1 steradian cone is the same quantity of light that the hypothetical melting platinum sends into a hemisphere by black body radiation. Well, divided by that factor of 60, which roughly equated the candela to the English candle power. So the light going into the cone from the point source times 60 equals the light coming from the black body. Write it this way, where the variable I sub cone represents radiant intensity of the point source, and I sub BB is the radiant intensity of the black body, with its flux filling a hemisphere as black bodies do. Break that down into the black body radiance times the source area. These lambda subscripts, by the way, remind us that these are spectral quantities, so intensity and radiance per wavelength. Let's go one more step and find the radiant power that the point source sends into the cone by multiplying intensity by 1 steradian, and then replace intensity with 1/60th times radiance times source area. Back to Smith's paraphrase. The lumen is the unit of luminous flux, watts, scaled by the human eye's spectral response to those watts, which is the connection we need between the lumen, photometric power, and the watt, radiometric power. By integrating the spectral power in the cone, weighted by the photopic curve, photometric power, or rather luminous flux, is realized. But this integral is declared to be 1 lumen. And I can pretty much assure you that after evaluating it, you won't get 1. So include a factor. Call it K. It's formally called the maximum luminous efficacy. We need to find that factor. What do you think it is? Well, the computed result won't be exactly 683. 683 is a legislated number. Any attempts to compute it will likely result in values that are off by, maybe a fraction or so of a percent. So go the warnings of everyone. Let's do it anyway. Blackbody spectral radiance is given by Planck's radiation law, which, by the way, I covered in an earlier video. Don't solve it analytically, of course, since V of lambda will be a data file, but organize this integral into a discrete sum and evaluate it numerically. I put in the values for the source area and the solid angle. Now all we need is a data set of the 1924 photopic curve, which was used in 1979 to surmise the scale factor of 683 lumens per watt. This is the 1924 CIE photopic curve, warts and all, including the notoriously incorrect short wavelength range. I wouldn't use it with a monochromatic blue source, but it's useful for full band calculations and still pretty widely used today. I found this data set in a couple of places. If you go to this one here at the bottom, you'll also find the updated photopic curves with the blue light corrected, but we need to use the 1924 data set since it was used to surmise the 683. So I pasted this CSV download into a spreadsheet that evaluates the integral numerically. So I added a third column with Planck's radiation law, and I've converted all of the wavelengths into meters, so I'm in MKS units. And then the product of the integrand, radiance times area times solid angle times the photopic curve times the discrete wavelength range. I evaluated it two different ways. One is with the left-handed rule and one's with the trapezoidal rule. Otherwise, that's the same column. Down at the bottom, I can see the results then. I just focused on the trapezoidal rule, not that it mattered. So the value of the integral, which is in the numerator, is divided by 60, and I get 684.569 lumens per watt. And that's using the 1924 photopic curve. I'm not sure why I didn't get 683, except for the warning that if you try to calculate the actual number, you're going to be off by a couple tenths of a percent in all likelihood. I did it again using the 1978 photopic curve, and I got 684.2. A bigger uncertainty can be introduced by your choice of the fundamental constants. So I used the 1979 values for the speed of light and Boltzmann's constant and Planck's constant. If I used earlier constants, like 1948 constants, I would have gotten 681.5. So there's a lot of variation around 683, hence the warning to not try to calculate it yourself. But at least now I see where it came from. I'll wrap things up with this pictorial summary. Say you measure a spectrum of the watts of light, and it looks like this. Units of watts per wavelength, and you want the total lumens of perceived light. Multiply by the photopic curve, which can dramatically alter the shape, then scale it by 683 lumens per watt, which locks it into a specific number of actual honest-to-goodness candles. The result is a reshaped and scaled spectral function, the lumens per wavelength. The total luminous flux then is found by integrating this curve over wavelengths, or in lay terms, and the punchline here, the area under this curve is the perceived lumens of light.